We will now be doing another lesson out of Classroom Mathematics. And we're busy with Chapter 12, Geometry of 2D Shapes. And today we'll be looking at Theorem of Pythagoras. So, with the Theorem of Pythagoras, we'll only be working in right-angle triangles. Now, in any right-angle triangle, the square on the hypotenuse is equal to the sum of the squares on the other two sides. So let's see what that means. If I have a right angle triangle and I call the hypotenuse side R, so just remember that the hypotenuse side is always the one that's opposite the right angle. And I call the other two lengths Y and X, then the theorem of hypotenuse, the theorem of Pythagoras, states that R squared is equal to X squared plus Y squared. So this is the relationship between these sides. If it's a right angle triangle, the long side squared will always be the two short sides added together, or the two short sides squared added together. Now, whenever you use the theorem of Pythagoras, you always have to state for your reason theorem of Pythagoras. Right, so let's look at an example. Example 1. So once again, I'm just going to draw the statement and reason, and then if I need to solve, so we need to calculate the length of xz. Now, since this is a right angle triangle, I can say that xz squared will be equal to, so this is my hypotenuse, that would be equal to these two short sides squared. So that would be xy squared plus yz squared. And this is then the theorem of Pythagoras. Alright, now we substitute the known value. So we've got that xz squared is equal to 8 squared plus 5 squared. And then I can solve for this xz squared. So xz will then be equal to, so this is where you can decide if you want to simplify this so long, or you can just type in the final answer in your calculator. I prefer doing that. The square root of 8 squared plus 5 squared. So this will then be equal to the square root of 8 squared plus 5 squared. And this gives us the square root of 89. Right, so that was example 1. Now for example 2, we need to solve one of the shorter sides. So once again, I've got my statement and reason. And if I put in since this is a right angle triangle, if I put in theorem of Pythagoras, the relationships AC squared, that's my long side, will be equal to the two short sides added together. So that would be AB squared plus BC squared. And then I say theorem of Pythagoras. Right, then I substitute in my known value. So I've got 15 for AC, so that's 15 squared, equals to, now AB is the one I want to solve, so I'm just going to say AB squared plus, and BC is 12, so that's 12 squared. All right, now to solve for AB, I need to take 12 to the other side, so that is 15 squared minus 12 squared equals to AB squared. Then AB square, or AB will be equal to the square root of 15 squared minus 12 squared. So if we type that in, we've got the square root of 15 squared minus 12 squared. And this gives me 9. Okay, so you can always always just write down the standard form and then do your substitutions and solve for the unknown. But an easier way to remember this is but this is also your choice if you'd rather prefer doing it like that. If I have my triangle x, y, r, and I need to solve one of the short sides. Let's say I need x. If I need x, then I have x squared equals the long side r squared minus the other short side. Or if I need y squared, I'll say the long side squared minus the other short side squared, which would be x squared. So you can actually just start off by writing this if you want to, just save some time of solving this, because then you just substitute your known values in here and take the square roots on both sides. But once again, that's for you to choose. So that was all the examples. This means you can now do exercise 12.2.